Good afternoon, sir.
Good afternoon. Good afternoon.
Good afternoon, sir.
What was the last thing we dealt with in your batch?
So you
If
solved
that
that
gravity
JEE main
is
You
question.
will start with electrostatics.
You
electrostatics, you have to
you
start.
did that JEE main question.
Okay. No, in your batch, did we calculate the field due to a solid sphere inside the cavity?
Yes,
Yes,
sir.
sir.
Yes, sir. Already done.
No. When should we be taking the doubts of gravitation? Do we have
For
a
you.
doubt?
You said
Last half an hour of
half an
this
hour.
week.
So tomorrow they have scheduled someone's doubt lecture, like some other teachers. ARP
Yes, sir.
sir.
Tomorrow ARP
Yes, for physics, I think it is.
Okay.
So I think he may take us the doubts of gravity.
Right. Keep me informed. On Sunday, I have scheduled a doubt lecture with flagship batch for gravitation.
Sir, you can also give that link to us.
Yes,
Right.
sir.
That you will have to remind me in the next class. When is the next class? Day after tomorrow.
Yes, sir.
So tomorrow, see what all doubts are cleared. Based on that, keep me informed. Sunday ka doubt lecture link, I'll send it to you people as well.
Okay, sir.
Existence of charge. Existence of charge. In gravity, you have only attraction. In electrostatics, you will have Q and Q will repel each other. Q and minus Q will attract each other. Like charges repel. Like charges repel. Unlike charges attract. Second most important thing, the least charge I can have. Charge is quantized. Charge is quantized. Charge is quantized. N into 1.6 into 10 raised to minus 19 coulomb. The least charge that I can have, positive or negative, is multiple times the charge of an electron. Charge of an electron is 1.6 into 10 raised to minus 19 coulomb. First of all, we will go into the details of Coulomb's law, which will be the same like that in Newton's laws. There it is Gm1 m2 by r square. Here it is kq1 q2 by r square. But electrostatics में categorical differences like charges repel, unlike charges attract. Now, coming to the first fundamental fact of electrostatics, prove the existence of charge. Prove the existence of charge. Generally, if you take a plastic scale and you rub it on your hand, the hair will stand. Only problem is I should wear slippers. The same thing when I used to do it in the classes, I used to wear shoes. So when I rub, this will stand, the hair will stand. You can show this even here. If I had longer hair, I'll show you a demonstration. First of all, I'll show you a photograph published in Halliday Resnick Walker. Halliday Resnick Walker. See the photograph of this girl. Are you able to see that?
Yes, sir.
Yes, sir.
Yes, sir.
Look at the way her hair is standing. I'll read out the para that he writes besides. The woman in figure 23-15 was standing on a lookout platform in the national park. where a large storm cloud moved ahead. Large storm cloud moved ahead. Some of the conducting electrons in her body were driven into the ground by the cloud's negative charged base. Some of the electrons in her body were pushed into the ground because of the cloud's negative charge base. Clouds can be positive as well as negative. Depends on the friction. Negative charge cloud moved close by to her. So the negative charge in her body got grounded, were pushed. Like charges will repel.
Yes, sir.
So now what did she have on the body? Positive charge.
Yes.
Now this positive charge will spread all over her body. The repulsion between the two hairs and the negative charge in the air made her hair stand. I repeat, originally her body was neutral. Because of the large electron cloud, the negative charge from her body was pushed into the ground. So now her body's surface has got positive charge. On the hair, there is repulsion between the positive charges and there is attraction between the positive charge and the negative charge cloud of the storm.
Yes.
Now our hair stands. Now I'll show you the photograph again. Have a look at it. Now you understand why the hair is pulled into the air.
Yes, sir.
Yes.
Right. Holiday Resnick Walker. People who are using this can see this photograph. Will it be true for anyone here? If you are filled with charge, your hair will stand. Ever walk very close to the TV? Do you feel
Yes,
that
sir.
being
Yes,
on the screen?
Sir.
Yes, sir.
Yes, sir.
Existence of charge. The air there is ionized. Air there is ionized. And the cloud is pushing the negative charge in your body to your left. The positive charge gets attracted. And hence you feel the hair on your skin is standing. Anytime you fill yourself with charge, your hair will stand. I'll show you one demonstration of Walter Levin. See this demonstration. There's one more important information given here.
Will be complementary to the book. If I added a, then I have to take the mass of the proton, which is 1.4. Then the acceleration that the proton will experience is the electric, but thank goodness the nuclear forces are not part of 802, so I'll leave that alone for now. So what holds our world together? Well, on the nuclear scale, 10 to the minus 12 centimeters, very important are the nuclear forces.
Unit mass. The Earth and Mars have each a charge of about 400,000 coulombs. The gravitational force between them is therefore about 17 orders of magnitude larger than the electric force.
If you people heard to this line, what did he say? The gravitational force is much, much higher than the electrostatic charge. There is a reasoning question asked in HCV picked up from university physics. The question asked is, what makes you feel that gravity is the force between moon and earth? Why not electrostatic force? Somebody is providing the centripetal force. Why not electrostatic force? He answered that question. The electrostatic charge on these planets is much, much, much lesser. What runs your celestial bodies is practically gravity. Right? He calculates this value also in this lecture slightly ahead. But right now our concentration is not on that. So let me go ahead, I'll come back to this at the right time.
So even though our immediate surroundings are dominated by electric forces, including your own body for that matter, the behavior of the universe on a large scale is dictated by gravity. We will use various instruments to measure charge in a quantitative way. And one of the instruments that you will see, we will use it often in the lectures that are to come, is called an electroscope. It's a very simple instrument. In general, it is just a conducting rod, it could be aluminum, metal, and at the end are two pieces of tinsel, two pieces of aluminum foil, and often there is a nice knob here. And if I touch this with a charged object, then because this can conduct electricity, this can conduct the fire, as defined by Benjamin Franklin, if I touch it with an object which is positively charged, then this object will become positively charged. If I touch it with an object which is negatively charged, it will become negatively charged. And you see now here these two very light pieces of aluminum foil will repel each other. And so you will see that this shows a certain angle. And the more charge there is, the larger that angle. So that gives us a way of doing some quantitative measurements. There are other electroscopes which are not too different. Just one central rod, and they would have one leaf hanging there. And when you charge that one up, then this leaf will go out, and if the charge is more, it will go out even further. I don't have an electroscope now here, but what I want you to see that if I charge myself up and I hold in my hand these Christmas tree tinsels, that in a way, if I get enough charge on me, then these tinsels will spread out. It's an idea that immediately follows from the fact that you get a certain amount of charge, whether it's negative charge for me or whether I'm positively charged, that doesn't make any difference. These tinsels will spread out. And of course, the best way I can do that is if I charge myself with the Van de Graaff. And as I said earlier, experiments of this nature are not entirely without risk. And so there's always the possibility, of course, that I don't survive this demonstration. But don't worry, because in that case there will be someone else who will lecture 802, except he is not likely to show this demonstration again. So you might as well take a close look, because this may be the only time you'll ever see it. So I will give you some nice light on the Van de Graaff. And it's always a scary moment for me. Sleepless nights about the Van de Graaff. Am I going to turn it on, Marcos, or you have the courage to turn it on? You will turn it on? Okay, hold it, Marcos. This is too close for comfort. You ready? Are you nervous? See you. So look at the tinsels. And try not to look at me, please. Go ahead. I am now a living electroscope. If the weather is cooperating today, and if I had long hair, you might even see that my hair would start to act like an electroscope. We can try that too. Why don't you throw it? Is it working? Okay, well, this weekend, make sure you take this nylon shirt off in front of the mirror and enjoy the experiment at home. Don't try this ever. See you Friday.
Now, if you people have observed, 1 second. If you people have observed this, generally your attention will be drawn towards the electroscope, or rather the thin cells which he is holding. When he touches this Van de Graaff generator, the equipment that he touches is called Van de Graaff generator, which is there in your syllabus, which will be taught to you once we are done with Gauss law in electrostatics itself. Right? That is something which is filled with charge. So when it is filled with charge, he stands on an insulating stand and is touching it. He will not stand on the ground and touch it. If he stands on the ground and touches it, the charge will be flowing through him into the ground. There will be a potential risk of he being electrocuted. That's why his assistant also doesn't hand over the wick to him. He throws the wick towards him. Because his assistant is standing on the ground. Hence, they should not permit the flow of charge. He stands on the insulating stand and then he touches it, then the switch is on. How do you know that the switch was on at this time? If you observe carefully, the moment the switch was on, there is small charged particles flying off the sphere. When the switch was on the upper part of the sphere, if you observe carefully, there are small charged particles flying off. I'll show you that again. Observe this, which we generally fail to observe.
Of your book, but they will be a matter of forces that I can do that. Sleepless nights about.
Now, after he gets on to that, and when the switch is on, observe the top part of the sphere.
So look at the tinsels.
Where he keeps his hand and above.
Try not to look at me, please. Go ahead.
Do you see here particles
I am
flying?
now a living electroscope.
Yes, sir.
Yes, sir.
Yes, sir.
If the weather.
Bottom line, they acquire the same charge and they repel each other. They acquire the same charge, hence they repel each other. So the dust particles also acquire the charge and they repel each other. Now, I don't know if you people have ever seen this program of Mr. Bean touching this Van de Graaff generator in a mall.
Yes.
There is a sequence.
Yes, sir.
Yes, sir, I saw that.
Yes, sir.
There is a sequence on which he'll have to do everything funny. His expressions are so funny that if you see kids laughing, they'll keep laughing, watching that. He wants to touch it, but a well-built guy there will stop him. There are 2 episodes of Mr. Bean dealing with Van de Graaff generator. In fact, he's teaching a very important concept of physics there. But no kid pays attention to that. They will be more engrossed into seeing his expression and laughing. He'll go around, he'll try to touch the, that's a small generator. What Walter Levin used is a big generator. Such big generators cannot be kept in public places. It will be dangerous. Somebody from the ground touches it, they'll be in trouble. No, it's a small generator with little amount of charge. So when Mr. Bean wanted to touch that, the well-built guy will stop him there. And he'll tell, climb on the dais, the insulating stand, and then touch. But as usual, Mr. Bean has to do something funny. He'll go that side, he'll go this side, he will try a number of ways of touching that. When he doesn't get any chance, he finally decides to come and stand on it. He touches that and he will have funny feeling expressions on his face, showing that charge gives him a jingling feeling on his face. There is an old lady who will draw the attention of this well-built guy, and immediately Mr. Bean will jump off and walk. He's not supposed to. The machine should be switched off. The charge should be grounded, and then he should leave. With charge over his body, he started walking. Then he attracts a piece of paper. The piece of paper sticks to his hand. That piece of paper then sticks to his leg. He tries to get rid of it in all possible forms. Then it sticks to his leg. He will do many funny things in that mall. He'll keep his legs in such a way, such that a very fat lady coming from the other side will stamp the other end of the paper. He will pull his leg out and he will walk away, assuming that the paper was held by the weight of that lady. In few seconds from then again, when he turns down and sees the paper is stuck to his leg, he is filled with charge. The paper will get attracted to him. In your schools, you people might have done this experiment. Take a comb your oily hair and bring it close to the bits of paper. It will attract.
Yes, sir.
He is filled
Yes,
with
sir.
charge. It attracts the piece of paper. He will do many funny things in the mall, and then finally he decides to hold himself and pull the paper out of his shoes. To do that, he needs a support to stand. When he holds a metallic support, now tries to pull the paper, he'll be amused to see that the paper is gone. Why? Because he held a metallic rod and he grounded himself. The charge on his body left through the metallic rod, and now the paper will leave him by default. Right? Ever if you watch this with your younger siblings or kids sitting and watching, try to ask them, why did the paper stick to him? They will be least interested to hear to that. His expressions are so well presented that they'll be laughing at him, but not learning the concept which that guy is trying to teach us. Undoubtedly, he's a very good actor. Right? Static in males after touching the railings. Yeah. Friction in so many forms will generate charge. If you people have ever seen you're wearing a fur coat, you sit inside the car and the car seat covers, if they are synthetic, after a long drive, when you get down, you try to shake hands with someone, you will find a small spark flying off your body. This is done in schools as well. You make one student sit in a plastic chair. Let his feet not be on the ground. Let his feet be folded this way. Hit the chair with a towel. If it is a woolen cloth, nothing better than that. And then you will see charge deposited. Sharper the edge, greater the charge density. Bring your finger close to his nose. You will see a spark flying from his nose to your hand. You generated charge over the body of the guy sitting in the plastic chair. How did you generate charge? By hitting it with a fur coat, or a towel also will do. Bush towel will do. Right? Hit and then bring your finger close to his nose. You'll see a spark flying. If the guy has a sharper nose, nothing better than that. Select a guy with a sharper nose to sit on the chair and hit the chair. You can try this at home. Just make sure that you are standing without slippers and the person sitting in the chair is not touching the ground. And you can see a spark flying from over his nose.
Why does friction generate charge?
Sharp edge, greater charge density. Friction is removing. You rub glass rod with fur, you are removing electrons.
Okay.
Sir,
Can I rub this part?
Yes.
sir,
Huh?
sir, is it due to existence of charge that lightning strikes on people?
Yeah. Lightning striking is purely flow of charge from higher potential to lower.
Oh,
Now, few general informations. What is a conductor whose resistance is less? Metals. Specifically, I am writing the example of water. Water, I am referring to the water that we drink, mineral water, has got salts and minerals which are available for conduction. Hence, the normal water that we drink is a good conductor of electricity. Normal water from the tap is a good conductor of electricity. Insulators, bad conductors, plastic, wool, any of these, and distilled water. Distilled water. Select distilled water. Distilled water, all the minerals and salts are removed. So it's a good insulator. Something more important is edible oil. Edible oil is a bad conductor of electricity. Edible oil is a bad conductor of electricity. In your home, if ever there is a short circuit, you should never throw water on it, because the water you have access to at home is the normal water, which is a good conductor. Readily accessible insulators at your home. You don't keep sand at home. Sand will be a very good insulator. At home, you will not get sand, but you will get edible oil, right? Edible oil, ghee, vanaspati ghee, palm oil, groundnut oil, till oil, refined oil. All forms of edible oil are very good insulators. Very good insulators, in fact. Groundnut oil and refined oil have some of the highest dielectric constants. They are very good insulators. So, you should never ever use non-edible oils like kerosene oil or petrol. Conductors of electricity. Not only that, they catch fire very easily. So, flammable, non-flammable are edible oils. Rather, they are good insulators. They don't permit flow of current in it. Salts and minerals increase conductivity of water due to their ionization. Once they have positive and negative charge, they are free to move. Once they are free to move, conduction is easily possible. Can I rub the board?
1 minute, 1 minute.
Sir, noted.
1 minute.
In the video, in the electroscope diagram, what did Walter Lewin drew on the electroscope? A ball-like structure he drew.
That is a hold. That is the metallic bob which is touched to something to get charge.
Achha, okay.
That's a knob, you can say. Somebody is asking boiling water. That is temperature dependence of resistance, nothing to do with it. Normal water is a good conductor, distilled water is a bad conductor. Now, when you raise the temperature, what will happen to the resistors? We'll discuss in current episode. Now, firstly, this is the way induction takes place. This is a metallic body kept on an insulating stand. You bring a glass rod rubbed with fur, positive charged glass rod. What will happen? By induction, the positive charged glass rod will attract negative charge here and it will repel positive charge here. It will attract the negative charge here and it will repel the positive charge towards the other end. The sphere was originally neutral. So first it was like this. Now you bought a glass rod charged with positive charge. This will attract the negative and equal positive charge is pushed to the other side. Then this part is grounded. When you have grounded that part and you kept the rod here as it is, the positive charge goes into the ground. The positive charge goes into the ground. Why didn't the negative charge also go into the ground? Because negative charge is bound by the glass rod. If by chance at this stage you remove the glass rod, even the negative charge will go into the ground. If by chance at this stage you remove the glass rod, the negative charge will also go into the ground. Who is holding the negative charge here? This glass rod is holding the negative charge. So now remove the ground connection. Now remove the ground connection. Right? Then last stage, remove the glass rod. The negative charge will get uniformly distributed all throughout the sphere. When I remove the glass rod, why will the negative charge get uniformly distributed? There is mutual repulsion between the negative charge. Right? There is mutual repulsion between the negative charge. So negative charge will always go to the farthest possible distance, which will be uniform distribution on the surface. And remember, glass rod is not touching the negative charge. If it touches, this positive and negative will partially merge. It is brought here close by so that by induction there will be negative and it will push positive to the other side. This is metallic. This is a metal. So glass rod should not touch the metallic sphere. If it touches, positive, negative will merge and nullify each other. Take it down till here.
Sir, could you please repeat what you said about the last two diagrams?
Once you have removed the earth connection, this will be the state. Positive charge went into the ground, you removed the earth connection, but you will keep the negative glass rod here that holds the negative charge. Without removing the earth, you will never remove the glass. You remove the glass rod here, the negative charge also will go into the ground.
Okay, sir, got it.
Now remove the glass rod, the negative charge will get uniformly distributed over the sphere.
Yes, sir, thank you.
Sir, in the fourth diagram, you removed the connection from the ground, na?
कनेक्शन दिख रहा है आपको?
अच्छा, okay.
अगर कनेक्शन है नहीं तो मतलब निकाल दिया ना यार.
ठीक है sir.
Done, sir.
Sir, if let's say the positive charge in the glass rod is in the less amount, so is this chance that some amount of negative charge will get grounded from the sphere?
Induction उतना ही होगा जितना positive charge can hold.
Okay, sir. So
When you bought, you are inducing charge. Generally, they'll be equal.
okay, sir. Got it.
Positive charge going into the ground is as good as equal negative charge coming from the ground and nullifying the positive charge. Both of them are equally viable. Either you tell me this quantity of positive charge went into the ground, or you tell me equal quantity of negative charge came and nullified this positive charge. Both the statements are equally right. Suppose I have two spheres touching each other this way. Now I bought the glass rod close by. I will have induced a negative charge here and positive charge here. They were touching. So positive and negative here merged with each other. Right?
Yes, sir.
Now what do? I will separate them. I will have equal positive charge here and equal negative charge on this. I separated them and removed the glass rod simultaneously. Right? So this negative charge will get uniformly distributed. This positive charge will get uniformly distributed. You have given two spheres two different charge. Now, based on this, try to design a system where you can give the same charge to both of them. Based on the same principle, try to design a system where you can give same charge to both of them. Draw this and then try.
Sir, can you repeat like what, like did you bring the glass rod and then separate the spheres?
I don't know what this. Bring the glass rod and then separate the sphere. Matlab,
Sir,
once
can
you
you
bought
repeat
the
the
glass rod, you will have negative and positive here, right?
Yes, sir.
हाँ, उसके बाद doubt क्या है? I removed this and separated them.
Okay, sir. Thank you.
Can I rub the board?
Yes, sir.
Yes, sir.
Now, when I want the same charge on both of them, I will ground this connection. See what is done. this is kept this way, and you ground this side. You will have the glass rod here with positive charge. You have negative charge here, and you grounded the other side, thereby you removed the positive charge.
Yes, sir.
Right? Now what will you do?
Remove the rod.
Remove the ground connection while the glass rod is yet there. Remove the ground connection when the glass rod is yet there. Now remove the glass rod. You will have negative charge distributed all throughout both of them. Now separate them. You will have two independent negatively charged spheres. If the spheres are identical, you will have the same quantity of charge. If not, it will not be the same quantity of charge. Here I grounded. Once I have grounded, the positive charge goes into the ground. Don't immediately remove the glass rod. Even the negative charge will go into the ground. So remove the ground connection first. Then remove the glass rod. The negative charge will get uniformly distributed all throughout. Somebody is typing, there is a video on the YouTube, signs of stupid short circuit. Let me see this. If it is related, I'll show you people. Naman, if I'm right. Then, sir. One second, wait. Now that episode goes on. Right. No, somebody is asking why didn't his hair stand up? Maybe whole of the charge was distributed over his body. He was wearing a coat and it didn't go till the hair.
Sir, he must have used a hair gel or something too.
Could be one of the reason. But then later on, when he brings his hand close to his ear, he hears to a resounding voice. Why? Now the charge is moving between his face and this. There is charge over his body. It's moving. That's the reason why he hears to the resounding voice. Now can I rub the board?
Yes, sir.
Sir, an alternate method for this could be if we brought the glass rod between.
Wait, 1 second, wait. Somebody said, did the charge flow to the ground when he walks on the ground? He's wearing shoes, no air. The moment he touches some metal, it will get discharged. Shoes are insulators. Flow of charge is not that easy. Yeah, somebody was telling an alternate method. Yes, there are alternate methods for this. You can ground this separately and get it done.
Yes, sir. We can bring the glass rod in between those spheres.
Yes. Now listen. Coulomb's law. Rather, the first thing we learn in electrostatics. Force is directly proportional to the product of the charges, inversely proportional to the square of the distance between them. K Q1 Q2 by R square. Vector notation for this will be K Q1 Q2 by R cube and the vector R. If I put a cap here, this remains as R square. This is in vector notation. What is the value of K? 9 into 10 raised to 9 Newton meter square by Coulomb square. Newton meter square by Coulomb square. Right? Newton meter square by Coulomb square. This value of K is 1 by 4 pi epsilon naught. Now here you are being introduced to a new variable called epsilon. Right now you will not get a complete understanding on what epsilon is. As days pass by in every class, we will keep adding some information to this. Slowly you will have a better understanding of what this epsilon is. But right now understand one thing. Epsilon is a Greek alphabet which represents a constant called absolute permittivity or permittivity of free space. Permittivity of free space. Epsilon is permittivity. Epsilon naught is permittivity of free space. Epsilon is permittivity. Permittivity of free space is epsilon naught. Value is 8.85 into 10 raised to minus 12 in SI units. 8.85 into 10 raised to minus 14 in CGS units. Epsilon naught is permittivity of free space. What does it actually measure? It gives you a raw measure of how much field is permitted through it. How much field is permitted through it. Don't ask me, tell me the measurements. In days to come, you will naturally understand how much field is permitted. Right now, F will be equal to 1 by 4 pi epsilon naught Q1 Q2 by R square in 8 or in free space. In A or in free space. Epsilon naught is permittivity of free space or absolute permittivity. Temporarily believe it is a constant. Value is 8.85 into 10 raised to minus 12 in SI units. What are the SI units? K is equal to this, right? So the reverse of this will be the SI units. K ka value is Newton meter square by Coulomb square. Epsilon naught will be reverse of this. Coulomb square by Newton meter square.
So we can't use the bottom right formula if the medium is different apart from air or free space.
If the formula will be different, I'll come.
Okay, sir.
Somebody now woke up in between. Now this person is asking, why does positive charge get removed when we grounded the sphere? Negative charge is held by the glass rod. Negative charge is held by the glass rod. That's why we said, do not remove the glass rod. The negative charge also will go into the ground. I'll send you the recording, see it. I repeated that statement multiple times. Can I rub the board?
Yes, sir.
Now suppose I select a dielectric medium. Dielectric medium. Dielectric means insulator. Could be distilled water, could be oil. And you keep two charges Q1, Q2 at a distance of r. What will be the force between them? Now Coulomb's law will become 1 by 4 pi epsilon r times epsilon naught. epsilon r is the relative measure of this dielectric material. Epsilon r is called relative permittivity or dielectric constant. It's a number, no units. Epsilon r will tell you it is 10 times epsilon naught, 20 times epsilon naught, 100 times epsilon naught, 500 times epsilon naught, so on and so forth. Q1, Q2 by R. If you place the two charges in free space, then it is 1 by 4 pi epsilon naught. If you are placing it inside a dielectric material, insulating material, then it is 1 by 4 pi epsilon r epsilon naught q1 q2 by r square. This epsilon r is relative permittivity or referred to as dielectric constant. And what is this dielectric? It is an insulator. It could be distilled water. It can be edible oil. It can be any form of an insulator. Now the force between them will be 1 by 4 pi epsilon r times epsilon naught q1 q2 by r square. And what does epsilon r measure? Greater the epsilon r, better the insulator. Greater the epsilon r, better the insulator. What do you mean by better the insulator? It cannot be converted into a conductor easy. Matlab, every material can be converted into a conductor. Yes. Just as you don't have a perfect conductor in the universe, you don't have a perfect insulator also in the universe. In general, air is an insulator. In general, air is a dielectric material. But when lightning strikes, charge is flowing through. That means at that instant, air has become a conductor. So every material forcibly can be converted into a conductor by ionizing the outermost electron. Best insulator known to us as on date is diamond. Best insulator known as on date is diamond. Just as we don't have a perfect conductor in the universe, we don't have a perfect insulator as well. Every dielectric material will have a dielectric breakdown. You can convert it into a conductor at some stage. What do you mean by dielectric breakdown? I'll explain. First of all, take it down till here. Only thing that epsilon r tells you is greater epsilon r, better the insulator or dielectric. Greater the epsilon r value. Epsilon r is a number, that's all. It may be 10, 20, 30, 50, 100, so on and so forth.
Sir, have you written the relative is it relative permittivity?
Permittivity, PERMI, relative permittivity or dielectric constant.
Sir, so in organic chemistry, I mean, water is the highest dielectric constant. So, sir, how it is then?
Distilled water. They are referring to distilled water. The mineral water or water available at home, you assume it is an insulator, you will be in trouble. That's why in schools it is taught clearly. In a short circuit, you are never supposed to pour water on a short circuit.
Yes,
Is this
sir,
taught
right.
to you people in 9th and 10th?
Yes, sir.
Because the water available with you at home is normal mineral water. It's a good conductor. Textbooks में water जब dielectric constant देते, they are referring to distilled water.
Okay. Then, sir, why fire brigade people use water then? If there is a
Fire
fire.
brigade people are not dousing insulator. Current की नहीं दिक्कत है नहीं, आग की दिक्कत है. Fire brigade people are bringing down the fire by bringing down the temperature.
Shock can happen.
You expect a fire brigade people to pour edible oil on the fire on the some 10th floor, 20th floor.
Okay, sir.
Heat and thermodynamic शुरू हुआ है आपका?
Yes, sir.
So in that case, Neil answer my question. If a chair is on fire, what is suggested we pour on it? Hot water or cold water?
Sir, cold water. Sir. Hot water.
If a chair is on fire, a non-living object, if it is on fire, Q is equal to ml. कभी देखा है formula?
हाँ
Yes,
sir.
sir.
That's
1 gram into 540 calories. This is the quantity of heat to vaporize 1 gram of water into vapor. Yes or no?
Yes, sir. Right.
Yes, sir.
Same 1 gram of water for it to rise the temperature from 0 to 100. How much heat do you need? Ms delta theta. 1 into 1 into 100. This is 100 calories.
Yes.
Matlab 1 gram of water to raise the temperature from 0 to 100 degrees Celsius, you will require how much heat? 100 calories. Same gram of water to be converted into steam, how much heat do you need?
540.
So now suppose this marker is on fire.
Okay.
If I pour hot water on it, every gram of water while evaporating will absorb how much heat from there?
540.
But if I pour cold water, how much heat will be absorbed?
100.
So I would prefer to pour hot water on a burning non-living object. Right? Then why don't fire engines use hot water? You didn't educate them, hence they're using cold water. No, they are aware of it that hot water is ideal. But the problem is, priority is to save life.
Yes, sir.
Somebody is burning inside a house, you go and pour hot water on them, doesn't make sense.
They will die.
Cold water, right?
Yes,
Because
sir.
you don't know 100% if there is somebody in the building or not. We can never say that. Hence, they will never pour hot water. But suppose if the marker or a chair, some non-living object is on fire, if you have access to hot water, but that's the second point. Hot water you will sit and keep boiling when something is on fire. We cannot wait for that instant.
Yes, sir.
If you have hot water, pour hot water on it. Every gram of water will absorb 540 calories while evaporating.
Okay. Thank you, sir, for the information.
Can I rub the board?
Wait, 1 minute, sir. Just a moment.
Okay.
Noted, sir. Done. You may rub it now.
So, but when we pour a cold water, then it would first go to 100 and then it will evaporate, right?
Yes. By then, उतना time कहाँ पर cold water नीचे गिर जाएगा. Droplets don't stand on that fire for long.
Okay, got it.
Need a lot of time.
Got it.
Now, what did we say? If you have charges inside a dielectric, the force on the two charges will be 1 by 4 pi epsilon r times epsilon naught. Q1, Q2 by r square. What is basically a dielectric or an insulator? Dielectric or an insulator, how does it behave? Why did it get the name di? Di in Greek representation is 2. Suppose I have an atomic structure like this. I have electrons going around the nucleus. This is atomic structure of an insulator. If I subject this to an external field, all the negative charge will come towards this. If I subject this to an external field, all the negative charge will come towards this. Yes or no?
Yes, sir.
Difference between a conductor and an insulator. The negative charge can be easily removed. It's a conductor. Insulator mein the negative charge cannot be easily removed. It will be held by the nucleus. So whole of the negative charge will appear to be concentrated here. Positive charge will appear to be concentrated here. I repeat this logic. Listen carefully. Conductor mein this outermost negative charge can be easily removed and that will be available for conduction. Insulator, this negative charge cannot be easily removed. It will be held by the nucleus. Hence, all of this negative charge will appear to be concentrated here. This is called a dipole. Di in Greek representation represents 2. Right? Di in Greek representation represents 2. Such type of materials with dielectrics when the dipoles align this way, this is called a dielectric material. How do I measure the dielectric? This is a better dielectric than that. Its value is epsilon r, dielectric constant or relative permittivity. It gives me a raw measure of how good an insulator it is. Suppose I have 2 dielectric materials. One is 10 epsilon r, one is 100. The one with 100 is a better dielectric material or a better insulator. And this word dielectric came from dipoles. The word di came from Greek representation of 2 poles, P-O-L-E-S.
So basically dielectric is another name for insulator.
Sir, can you repeat what have you written there? Dielectric.
Dielectric material.
Oh, okay, sir.
Done, sir.
Somebody
Sir,
is
if
saying,
a
sir, will epsilon depend on number of dipoles? It will not. Epsilon doesn't depend on the number of dipoles. It rather depends on how much electric field you need to bring out an electron. Epsilon r will rather depend on how much. See, there is no perfect insulator. Now, what did you tell me? These electrons are not pulled up. But suppose I start increasing the electric field. At some stage, I will pull out an electron. That electric field at which I convert this into a conductor is called dielectric breakdown. That external field at which this is converted into a conductor is called dielectric breakdown. Breakdown doesn't mean you broke the material. Breakdown means it became a conductor. Right? So, epsilon r will depend on that electric field. Greater the electric field required to convert it into a conductor, greater will be the epsilon r value. Right? Just for your idea, I'll give you the values of few epsilon r and dielectric breakdown.
Sir, so we can say that greater the lesser the epsilon value, the better the conducting capacity, right?
Why do you want to put it in conducting? Put it in non-conducting.
Oh yeah, sorry.
Epsilon r, better
Yes, sir. That's what I meant. I just said the opposite. So sorry,
yeah.
sir.
I'll put a few values on the board for your understanding. They're actually given in every possible textbook. Appendix of every textbook it will be given. Mica sheet, epsilon r value and electric field. This is called dielectric breakdown. Dielectric breakdown. That means that value of the external field at which the material is converted into a conductor. Mica sheet is between 3 to 6. Epsilon electric breakdown is 12 volts per millimeter, if I am right. Sorry, kilovolts per millimeter. How do you measure field? Field was V by R. Do you remember this?
Yes, sir.
Yes, sir.
So it is volts per meter or volts per centimeter or volts per millimeter. It is kilovolts per millimeter. You apply this amount of electric field, mica sheet is converted into a conductor. These electrons are pulled up. Let me give you one more example of glass. Glass, right? 3.40. This is, sorry, bakelite. Bakelite, how much is that? 4.9. 4.9. This dielectric breakdown is bakelite 24 kilovolt per millimeter. So technically take this as 3. 6 is a different type of mica sheet. So when epsilon r is 3, dielectric breakdown is 12. When bakelite epsilon r is 4.9, this is 24. Right? Now give me some more examples. Quartz 3.8 is 80. Paper 3.5 is 14. Paper 3.5 is epsilon r. Kilovolt per millimeter. Right. Strontium titanate, titanium dioxide. So different materials have different. There are huge number of exceptions also. Remember this. Sometimes there are exceptions where epsilon r is very high and dielectric breakdown will be low. There are exceptions. And exceptions are quite a few, not one or two. But a general raw understanding is better the epsilon r, better is the insulating material or dielectric constant. Diamond ka value is not given here. Somebody is asking diamond. We'll have to Google search.
So
Is
we have to
stable or
remember
permanent?
this.
Pardon?
We got to remember this.
No.
Oh, all right.
We will not require this. It is just for your understanding. Somebody asked the value, so I put.
Sir, diamond is 5.7.
Yes, sir. 5.
Epsilon r.
Sir.
Yes, sir.
Yes, sir. And 1
Why
million
so
volts per
high?
centimeter.
And how much is the dielectric breakdown?
1 million volts per centimeter.
1 million, 10 raised to 6 volts per centimeter. Am I right?
Yes,
1 million is 10 raised to 5 or 10 raised to 6?
6.
6.
Abnormally high value. Some of the best insulators are made of diamond. No.
Can a lab go to such a level of volt electric field? Like for a diamond?
Very difficult to generate. 10 to the power 6 volts per centimeter will be too high. But by then diamond will change its structure. No point. For example, wood, if I expose it to high electric field, it will be converted into ash. It gets burned. So it will not remain as wood. The identity of the material changes. Now, listen. Next class, we'll be starting with electrostatics, which will start matching with gravitation, which we have done. Potential, field, potential energy for an extended body, ring, so on and so forth. So much of that time will be saved for us. Homework for you people will be, please read electrostatics from Halliday Resnick, Crane or Walker. Either of the two books. From this chapter, reading Halliday Resnick is mandate. Is this instruction very clear to all?
Yes, sir.
Yes, sir.
Yes, sir. Yes.
This is a big chapter. Electrostatics is a big chapter. Uske baad fir chapters become small till we come to EMI. EMI is then one big chapter.
Sir, I had one doubt. Like in chemistry, we say water has a higher dielectric constant, so it dissolves ionic salts here, like more. So, like, what's the reason for that?
Ask your chemistry.
Okay.
Sir,
do we need to
maybe
read full
disperse or we
HR
got
by
to
next?
wait. Sir, may we disperse or we have to wait?
Yeah, you can discuss.
All
Sir,
right.
do we need to
Bye,
read
sir.
full HRK by next?
No. Read the first few introductions. Today we just introduced.
Sir, which is the latest edition of volume 2? Like we have to, which edition do we have to buy for volume 2?
5th edition is available. Other editions are not even in print.
Okay, sir.
The latest edition of Halliday Resnick, Crane is 5th edition.
The dolphin
I
one, na?
think 12th or 13th edition has come out.
So,
Walker
we
has
should,
only one volume.
so for volume 2, we should take only the Halliday Resnick Crane, right?
सिर्फ क्रेन का 2 वॉल्यूम्स है, वॉकर का एक ही वॉल्यूम है, वॉल्यूम 2 है नहीं.
Yes, sir.
Walker, whole of that has been put. What I have is the 10th edition. Whole of this is put in one volume. I have 10th edition. Now I believe 12th edition has come out. Right? But Crane ka, the 5th edition only is available. There are 2 volumes, volume 1 and volume 2 for Crane.
Sir, I had a small doubt, sir. In the place of a dielectric material, if you have kept a conductor there, would the diagram have looked different? Or would it have looked same, just ER value would have been
It
same?
will look different because these electrons can be removed from this nucleus. So dipole will not be formed at the first place. If I keep a metal, these electrons are bound by this nucleus, makes it a insulator.
Okay, sir. That's why only in dielectric materials the dipole are aligned. Okay, sir. Got it.
So what are the units of dielectric breakdown?
Dielectric breakdown is electric field. Electric field. Volts per centimeter, volts per millimeter, volts per meters. SI units is volts per meter.
Sir,
greater the ER, better the insulator is just a raw statement. There are
Just a
exceptions
raw
to it, right?
statement. There are quite a few exceptions.
Okay, okay, sir. Thank you.
See you people in day after tomorrow's class. Good day. Bye.
Bye, sir. Thank you, sir. Have a good day.